So let me try to emphasize what we are trying to do here. Um, we have a matrix which is the n matrix, which is the instance matrix. But somehow we only focus on the matrix that taking out the first row. And for the Cauchy-Binet formula, sometimes we just pick some of the submetrics and try to calculate the determinant. And in this case, we just take alpha is equal to these four edges. Just look at the graph. It looks like it is a spanning tree, right? It is a spanning tree. But if we come back to look at number 3, 4, and 5, and 6, this part of the submetrics, it looks like this. Okay, and this one is not quite hard actually. If you move the last column to the first one, the determinant will swap by the determinant will be the sign will be swapped. But after you move into that moving the last column to the first column, then it becomes a lower triangular matrix, and all the diagonal entries are 1 or minus 1. So you can see that the determinant of this guy is equal to 1 or minus 1. And somehow there is a wiser way to construct this kind of upper triangular or lower triangular. The reason is here. Let's look at the tree on the top right. One is the vertex that is taken out, right? So you see there is no 1 in the rows. 1 is taken out, and going from 1, then we have E5, and it is connected to 5, and we also have a new vertex which is 2, and it is connected by E6. So let me draw everything in a different way. Okay. The order is how we explore the new vertices. Okay, we start with the 1, which is something that is missing, but we use the edge E5 to go to vertex 5. And we can use E6 to find out vertex 2, and then you use E4 to find out vertex 4, and use E3 to find out vertex 3. It is a tree, so you will visit all the vertices just exactly once, and then you will see that using this order, E5, E6, and then E4, E3, E5, E6, E4, and E3, then it will gives you some nice structure. And after some permutation, it becomes a matrix of determinant equal to 1 or minus 1. And so we know it is equal to plus or minus 1. To have a closer look of this one, E5, it is supposed to connect 1 and 5. 1 and 5. So there is a 1 here. It is nothing on the other side. But for E6, it is connecting something from the above and explore a new vertex 2, something to 2. So there is a 1 here. And E6 does not go to any vertices at the bottom. E4 goes to number 4, but nothing to the bottom. E3 goes to number 3. So it will automatically create this axion form structure to help you to calculate the determinant. That's basically the idea behind the proof that if it is a spanning tree, then the determinant is equal to 1 or minus 1. Okay, so I want to continue with the next topic, which is the effective resistance. and it is something from physics. Oh, I forgot to let you read something. Anyway, I will continue, and later on, if you find some hard words there, then we can discuss, or I can just explain that in the class. Okay. So before doing this, again, I need to introduce one new idea in linear algebra, and may or may not you have learned this. It's called Moore-Penrose inverse. Pseudo inverse. And okay, because I still have that, so it is easy to calculate this weird inverse. You just do pseudo inverse, then it will try to help you to calculate that. But notice that L is not invertible. L has nullity equal to 1, but this pseudo inverse works no matter the matrix is invertible or not. But we will come back to the code later, and let's look at the theoretical part first. This notion of inverse works on any matrix, M times N matrix. It needs to work on the inner product space, but it doesn't matter. For R, everything is good. So we can consider one function that is sending the Rn to Rm by sending the vector u to A times u. This is a natural linear function associated with A. Now let's try to visualize this function. So after sending everything, this is Rn to Rm, then there is a 0 in Rm, right? And there is a subspace in Rn. We call that as kernel. And kernel is the subspace that's sending everything to 0. Okay, everything in here will vanish, will become 0 after sending that to the other side. This is the definition. On the other side, we know something more, which is called the column space. Okay, the column space is something that you can send to everything, the range of the function. So it is also equal to the range of Fa. So what does that mean is everything here you can find a vector sent to this sent to this point. Okay? Now we can do some geometry on here. This is kernel, right? And so kernel is orthogonal to the other space, which is called the row space of A. Row and kernels are orthogonal. And on the other side, we also have something called left kernel. So this is the kernel A transpose. We call that as the left kernel. So what happens here is if you send everything from Rn to the other side, it is quite likely that there are something that will disappear after you send in the function. This will disappear, and we call that as the kernel. But on the other side, if you look at the row space, it seems it is good that how to say that? If you pick one row space, then sending to here, it is not going to become 0, right? And in fact, what happens here is FA is not always invertible. Of course. But somehow, if you focus on the function FA, focus on the row space of A. Okay? And row space of A, whenever you pick a function, you pick a vector in the row space, and then you will send that to the column space of A. Because column space is the range. So we just limit our domain on the row space. So this one is actually always invertible. So that's the main idea in this picture. Whenever you have a linear function, you will have some kernel, and also the kernel will say that this function is one-to-one or not. If you take out the kernel, then it is one-to-one. On the other side, for the codomain, beyond the range, there is something else that is useless. If you take out this part, then it is actually an onto function, or surjective function. So the idea is if you take out this one, it is one-to-one. If you take out this one, then it becomes onto. So if you only consider the function that's sending this plane to this plane, the row space to the column space, then you can take care of, you can carefully prove that it is invertible. It is a one-to-one and onto function. It is a bijection. And more than that, this is they have the same dimension, right? And their dimensions are equal to the rank. Okay, so that's the main idea here. Let's call that as R sending to C is equal to AR. Okay. So that's the idea. Now we are able to define a new function which we call the f-Dagger. Again, not the standard notation. If you just do Dagger in LaTeX, then you will be something like this. You will see it is kind of really like a knife. So Dagger means 短刀啦，匕首，只有在游戏上才会出现的东西。Okay, so this f-Dagger is going to be the inverse function that we are looking at. Although f does not have the inverse function, but we can kind of create one. The idea is the following. The inverse will send in Rn back to Rm. If you look at Rn, then it is the column space of A, direct sum with the left kernel. Well, so on the other side, the Rm is equal to the row space, direct sum with the kernel. So what we're going to do is pick one vector in the column space and pick one vector in the kernel space. These two vectors is enough to represent all the vectors in Rn. Okay, so every matrix of this form, we are going to send that to R, such that AR is equal to C. And R is in the row space. So basically, we mentioned that row space and the column space has a one-to-one correspondence, right? So F will send R to C, f-Dagger will send C to R. F will send the kernel to 0. F dagger will send left kernel to 0. So that's pretty much it. Let's copy the picture again. This is F. So what happens is, if you have F dagger, then you will send everything to the left hand side, but this part will goes to the 0. And that's all. As long as you know this mapping, then you are able to calculate A and A dagger. The pseudo inverse of A is the matrix representation of F dagger. So overall, the idea is simple. Ignore the kernel, ignore the left kernel, and just focus on the row and columns. Row space and column space, they have a one-to-one correspondence, and try to make it as a function. But this is not easy to calculate, right? So let me give you some basic formulas. If D is equal to D1, D2, up to Dn, it is a diagonal matrix. Then D dagger is equal to D1 dagger, D2 dagger, and up to Dn dagger, where these numbers are easy. Di dagger is equal to Di 1 over Di if it is invertible. Otherwise, just set that as 0. Okay, so quite simple formula. You look at the diagonal matrix, you see whichever it is invertible part, we just make it invertible. If it is 0 that belong to the kernel, then we just ignore that, keep it as the kernel. That's the pseudo inverse, the idea of the pseudo inverse. So for symmetric matrices, say M, and we can write M as the diagonal. We can diagonalize this matrix QDQ transpose. Then M dagger is equal to the same thing, but now we want to make the D into dagger. This is how we calculate the pseudo inverse for a symmetric matrix. It is, the theoretical part is a bit long, but all we want to do is just do this thing. Make the diagonalization, and for the D, do the inverse if possible. Okay. In general, if you have a matrix which is sigma 1, sigma 2, up to sigma r, this is the singular value decomposition, the form in the singular value decomposition. You have a lot of zeros here. Then its dagger is equal to just the inverse of that. Okay, and any matrix has a singular value decomposition. M is equal to U sigma V transpose. then m dagger is equal to let me make it right. M, N, N, M. Okay, you have to do the transpose. And to do the transpose, you need to do the V sigma dagger and U transpose. Okay, forget about this part. I'm not quite sure about this part. But in general, you can find the pseudo inverse by using the singular value decomposition. Okay, so anyway, if you are doing the homework, you can use the computer program to calculate your pseudo inverse. So it is not too bad. Again, I am going to screenshot this part. Okay, I want to just emphasize the last part, and then we're basically done. Maybe without too much explanation. A circuit, what I meant is 电路图, like a power network. And this problem will happen in your high school physics course. Here is some example. If you have two wires, 两条电线, and their resistance, 电阻, wire is the line connecting the two components, and the resistance is just the physical term that usually we write it as R, and V is the voltage, right? V is kind of the pressure, what is the momentum at that point. And we also have the current, V and I. Current just means how much you flow through, how much the electricity flows through a wire. So I'm not sure how you learned that, but basically there is a formula saying V divided by I is equal to R. Right? So that's the things that we are talking about today. So suppose that R is equal to 1, R is equal to 1 for these two wires. Then we can think of what is the resistance between them, right? We call this as a series. And we know it is, say, R1 and R2, then the resistance is equal to R1 plus R2. And we also have the other case, which is like parallel. We have some current flow from the left to the right, and we have R1 and R2. And in this case, we call that as parallel. And in this case, R is equal to a weird formula, 1 over R1 plus 1 over R2, and then take the reciprocal. Anzi, have you seen this before? Yes? Okay. Okay, just want to make sure that we are using something similar, the language. I'm just going to pose a question and then give the answer, and without too much explanation. Okay? So, the question is the following. If you know there is a 1 amp going inside and then flow out from the right hand side, and assuming all the edges has resistance 1, okay, so then the question is, if you go from this side to this side, what is the resistance? If you consider the whole thing as a component, what is the resistance of that? And by this, I mean you have to look at the potential here, V1, and you have to look at the potential here, V2, and try to calculate the V1 and V2. Then the resistance is equal to V1 minus V2 divided by the current. And we call this as the effective resistance, 有效电阻. It just means that the whole thing, what is the resistance of that? So that's the question, and here is the answer. Let L be the Laplacian of the circuit. And we call this vertex as I, this vertex as J. Then we can do L dagger, the pseudo-inverse. This is a theorem, I guess. The theorem is the following. The effective resistance from I to J, it depends on the vertices that you want, right? From I to J is equal to this formula, EI minus EJ transpose L dagger EI minus EJ. And here EI is equal to all zeros and with the 1 at the ith position. Okay. So let's see. Let me say one more, and then we are done. Okay. We use this example. The Laplacian, let me call that 1, 2, 3, 4, 5, 6. The Laplacian looks like this, and we want to input some current inside, and output some current. Let's consider V is a vector in R6 recording the potential at each vertex. Okay, so basically we call that V1, it is the potential there, V2, V3, V4, and we know if the potential V1 is higher than V2, then the flow will go from left to the right. The potential will flow from higher to lower. Okay, and in this case, V is just equal to a vector, which is called V1 up to V6. And this is the theorem says that L times V1 up to V6 is equal to 1, 0, 0, 0, 0, minus 1. And notice that this is EI minus EJ. So what does this mean? It means that if you set this inside, okay, we have 1 here and then minus 1 here. It indicates how much current you want to input to this circuit and how much current going out. And the Laplacian is providing an important tool that it will transform the potential into the current outside. And it is a bit technical, so I don't want to describe all the details, but basically it is transforming V1 to V6 to something like here. Okay, now you might notice that L is not invertible, so this is not always solvable. But the only kernel of L is equal to the O1's vector, which is orthogonal to this one. And therefore, actually, this quantity is always solvable. You can find out the potential of this guy. So let me show you an example. Okay, we have a 6, and then 0, 1, 2, 2, and 4 is connected. You can still show the graph in the console, but it will take a while. Okay, never mind. I'm lying. Okay, here. So I made it wrong. 0, 1, 2, 2, and 4, right? One and 4. So let me start over. L is equal to G dot Laplacian matrix. It looks like what we wrote before, and let's say EI minus EJ, EI is equal to the vector of 1, 0, 0, 0, 0, minus 1. Okay, this is EI minus EJ. Now we can do L dot pseudo inverse and then multiply by EIEJ, then that will be the solution. Okay, so you will see that the current, the voltage looks like this. Let me copy it to the other side. let me finish writing the number and then move it to the next page. One is 11 over 30, and then 2 is 1 over 10. Let me just write it as 3 over 30, 3 over 30, and minus 1 over 30, minus 3 over 30. And the last one, minus 11 over 30. Okay, and then let me move this to the other side. Okay, and then you can see that these numbers are the potential. It will keep dropping from 11 over 30 drop to 3 over 30, and it does not change up to here, and then drop to minus 11 over 30, and then it keeps dropping. So if you go from the left to the right, the potential drop is 22 over 30, and so you can see the V1 minus V6 is equal to 22 over 30, and then V1 minus V2 over the current, which is equal to 1, is equal to the same thing. And this is the effective resistance.